There is a mark on your keyboard that almost did not survive the 17th century. Why did a book printed in London in 1557, carrying what turned out to be the most useful invention in the history of written thought, go through exactly one edition and never get reprinted, while its author's other books ran to 47? What does a failed silver mine in County Wexford have to do with the algebra you were taught at 14? And why did one of the finest mathematicians of the last 50 years spend the final decade of his life arguing that the equals sign, written the way every single person writes it, is quietly wrong? Those three questions have the same answer, but the answer is not really about mathematics, and by the time you can see how they connect, the thing bothering you will not be the history. It will be what the history implies about the Marx you are thinking with right now, tonight, in this room. Get comfortable. Stay to the end, because you will understand why the symbol you have written 10,000 times was never chosen for being right. Ad-free episodes live over on our Patreon, Meridian Labs, which sits behind this channel and a handful of others like it, along with early access and the full source archive for every episode. Subscribe or join if you have not. Let's start where it started. Every equation you have ever written contains a dead man's handwriting, not as a metaphor, as a physical fact about the marks on the page. Those two short parallel lines you draw without thinking, the mark you first copied off a blackboard when you were 5 or 6 years old and have now made somewhere in the tens of thousands of times since, was drawn for the first time by one specific person. In one specific book, printed in London in the year 1557, his name was Robert Recorde. He was Welsh. He was a physician who had run the Royal Mint at Bristol, and within about a year of that book coming off the press, he was dead in a debtors' prison on the south bank of the Thames, owing a sum of money that the Crown, at that exact moment, owed to him. The book was called The Whetstone of Witte. Of everything Recorde wrote, it is the only one nobody bothered to reprint. The mark is 469 years old. That is the whole of it. Human beings had been doing mathematics for something on the order of 5,000 years before anyone wrote down a symbol for equals. The Babylonians were solving quadratic equations on wet clay in the 2nd millennium before the Common Era, and they did it without the sign. Euclid wrote the elements without it. Archimedes computed the area under a parabola without it. Al-Khwarizmi, working in Baghdad in the 9th century, invented the entire discipline we now call algebra, gave it the name it still carries, and never once had a way to write the single most common relationship in the subject he founded. He wrote the word out, every time, in full, in Arabic prose. The pyramids at Giza are older than the equals sign by roughly 4,000 years. The equals sign is younger than the printing press by more than a century. It is younger than the Church of England. Shakespeare was born 7 years after it appeared. Isaac Newton was born 85 years after it appeared, which means that when Newton was a boy learning his letters, the symbol at the heart of every equation he would ever write was less than a century old and still, in large parts of Europe, losing. That is the part I want to sit on, because it is the part that gets left out of every telling of this story. The equals sign did not arrive and get adopted. It arrived, and then it vanished. After Recorde printed it in 1557, the symbol did not appear in another printed book for 61 years. 61. A man could be born, live an entire adult life, and die of old age in the gap between the invention of the equals sign and the second time anybody used it. And when it did come back, it came back into a fight it very nearly lost, against a rival symbol invented by the most famous philosopher in Europe, propagated by the best mathematical publishing operation on the continent. and preferred by a large fraction of the working mathematicians of the 17th century. There is a version of history, not a distant or improbable one, in which you learn to write equality as a small backward loop, and the two parallel lines are a footnote in a book about failed notations. I have spent an unreasonable amount of time in this material over the last stretch of weeks, and the thing that has stayed with me is not the trivia. It is what the trivia forces you to consider. Because if the symbol was almost never adopted, and if mathematics was demonstrably slower and heavier and harder without it, then a question opens up underneath the whole enterprise that I do not think has a clean answer. How much of what you experience as thinking is actually being done by the marks? Not by you, by the notation. By a set of squiggles that some specific human being decided on for reasons that were sometimes brilliant, sometimes commercial, sometimes an accident of who happened to know whom, and who died before finding out whether the choice stuck. That question is going to stay open for the next 2 hours. I am not going to close it, because I do not believe it closes. Let me start with what actually happened in the room. The book is a sequel. In 1543, Recorde had published an arithmetic textbook in English called The Ground of Artes, and it was a genuine commercial success, one of the most reprinted mathematical books in the language. The Whetstone was meant to be the follow-up, the second part, the one that took a reader who could already handle numbers and walked him into the strange new territory the Italians and the Germans had been calling the cos. The word is worth a second. Cos comes from the Italian cosa, meaning thing. In early algebra, the unknown quantity was called the thing because nobody had a better name for it. The Germans took the Italian word and built an entire tradition around it, die-cos, Cossack algebra, and the practitioners were called Cossists. Recorde, writing in English for an English readership, called the title of his book a whetstone, and if you know that the Latin for whetstone is cos, you have just watched a 16th century Welsh physician make a bilingual pun in the title of a mathematics textbook. The book that sharpens your wits. The book about the cos. The same word. I mention it because it tells you something about the man. He was showing off. He was enjoying himself. He was writing the first English algebra book in history, and he opened it with a joke that only worked if you had Latin and Italian, and then he wrote the whole thing in the vernacular for people who had neither. The equals sign appears about 2/3 of the way through, in a section headed the rule of equation, commonly called Algebra's rule. The sentence, in his own spelling, runs like this. And to avoid the tedious repetition of these words, is equal to, I will set as I do often in work verse, a pair of parallels or Jamoe lines of one length. Thus, and then he draws the sign, and then he explains why. Because no two thinges can be more equal. Read that again, because there are two separate things happening in it, and only one of them ever gets quoted. The famous half is the justification. No two things can be more equal. It is a lovely line. It has been reproduced on posters and in textbooks, and on the plaque in St. Mary's Church in Tenby, where they eventually put up a memorial to him. It sounds like a philosopher's argument. It sounds like Recorde chose the symbol because it embodied the idea of equality itself. Two identical lines, perfectly matched, neither one above the other. The other half is the reason he actually gives, and he gives it first. To avoid the tedious repetition of these words, is equal to, he was bored. That is the origin of the equals sign. A man was writing out the phrases equal to by hand, over and over, in a manuscript he was preparing for a printer, and he got sick of writing it. And he invented a mark to save himself the labour. The philosophical justification comes second, in the subordinate clause, as the explanation for why he picked those particular lines rather than some other shorthand. The primary motive is that his hand was tired. I find that clarifying rather than deflating. The single most important symbol in the history of formal reasoning was invented as a labour-saving device by a man who had a deadline. There is a detail here that almost nobody mentions. Recorde's original sign was not the compact mark you use. It was long. Substantially longer than modern typography, a pair of parallel strokes that stretched across a noticeable fraction of the line. He also uses the word gemoe, which is not a word anyone has used in centuries. It comes through French, gemot or gemelle, from the Latin gemellus, and it means twin, the same root that gives us Gemini. He is not calling them parallel lines, he is calling them twins. He then does something that suggests he had thought about this more carefully than the passage lets on. He uses the sign immediately, in a run of worked examples. The first of them, translated into the notation you already know, says 14 times the unknown plus 15 equals 71. That is the first equation in the history of printed mathematics to contain an equals sign. You can solve it in your head in about 4 seconds. The answer is 4. 4 seconds. Hold on to that number, because we are going to come back to how long that same problem took to state and solve before the mark existed, and the comparison is not close. The Whetstone does one other thing that nobody credits it with. It is the first book in the English language to use the plus and minus signs. Recorde introduces them almost in passing, saying that there be other two signs in often use, of which the first is made thus and he draws the cross, and better caneth more, and the other is made thus and he draws the stroke and better caneth less. He did not invent those. He got them from the continent, and the place they first appear in print is a book by Johannes Widmann, published in Leipzig in 1489, with a title that translates roughly as Nimble and Neat Calculation for All Trades. That book is not a mathematics text, it is a commercial arithmetic, written for merchants. And in it the cross and the stroke do not mean add and subtract, they mean surplus and deficit. They are warehouse marks. A barrel comes in weighing more than the standard measure, and you write the cross beside it. It comes in light, and you write the stroke. The two most common operational symbols in the whole of mathematics began life as annotations on the side of a barrel in a German warehouse, and it took about 70 years for anyone to notice that the same marks would work for the operations themselves. I keep finding this. Every time I go looking for the origin of a symbol, expecting a mathematician with a theory, I find a person with a practical problem and no idea what they have just done. But here is where the story stops behaving the way you would expect, and this is the first crack in the tidy version. Recorde was not necessarily first. In the library of the University of Bologna, there is a manuscript described by the historian Ettore Bortolotti and reported by Florian Cajori in his History of Mathematical Notation, in which two short parallel lines are used as a sign of equality. The manuscript is dated to somewhere between 1550 and 1568, which means it might predate the Whetstone by 7 years, or postdate it by 11, and there is no evidence of contact between the two. Nobody in Bologna was reading an English algebra textbook in the 1550s. English was not a language European mathematicians bothered with. Two people, in two countries, with no connection, reached for the same mark within a couple of decades of each other. That should bother you slightly, and it is going to bother you more later, because it cuts against the story I have just told you. If the equals sign was a stroke of individual genius, why did it occur to more than one person? And if it was obvious enough to occur independently to two people in the 1550s, why did it not occur to anyone at all in the previous 5,000 years? I do not have a clean answer to that. I want to be honest about it now rather than pretend later. What I have is a suspicion, and the suspicion is that something changed in the middle of the 16th century that made the symbol thinkable, and that the thing which changed was not mathematics, we will get to what I think it was. For now, hold the shape of what has happened. A man in London, sick of writing a phrase, invents a mark. He uses it 6 times. The book sells badly enough that it is never reprinted. He dies in prison the following summer. And then, for 61 years, the most important symbol in the history of human reasoning sits in a single unpopular book, in a language almost no mathematician in Europe could read, waiting, to understand why that waiting matters. You have to know what it was actually like to do mathematics without the mark. Not in the abstract, not as a sympathetic thought experiment, in the specific, physical, sentence-by-sentence sense of what came out of the end of a pen. Here is a real problem from the book that named the field. Around the year 820 in Baghdad, a scholar working in the House of Wisdom wrote a treatise whose short title is Algebra, the Restoration, from which we get the word algebra. His name was Muhammad ibn Musa al-Khwarizmi, and a Latinized version of his name is where we get the word algorithm. He is not a minor figure. He is the origin point of 2 of the load-bearing words in modern technical vocabulary. In that book, he poses the problem that we would write as x squared plus 10x equals 39. Here is how he had to write it. A square and 10 roots are equal to 39 dirhams. That is not a translation into plain English for your benefit. That is the mathematics. That sentence is the equation. There is no other version of it in the manuscript. The square is what we call x squared. The roots are what we call x. The dirham is the unit, the plain number. The relation between them is carried by the words are equal to spelled out, because there is nothing else to carry it. Now here is the solution, and this is where it stops being a curiosity and starts being a problem. You halve the number of roots, which in the present instance yields 5. This you multiply by itself, and the product is 25. Add this to 39, and the sum is 64. Now take the root of this, which is 8, and subtract from it half the number of the roots, which is 5. The remainder is 3. This is the root of the square which you sought. That is the quadratic formula. That paragraph in words is the thing you learned as a single line of symbols in about 90 seconds of a Tuesday afternoon when you were 14. Al-Khwarizmi could not write it as a formula. Nobody could. There was no formula, because there was no notation in which a formula could exist. There was a procedure, described in prose, that you memorized as a sequence of instructions. The way you memorize a recipe. And notice what is missing from it. There is no way to see that the procedure is general. In symbols, you can look at the completed square and read off, immediately and visually, that the method works for any coefficients at all, because the letters are placeholders and the structure is visible in the shape of the expression. In prose, you get one worked example and a promise. You have to trust that the same words will work with different numbers. You cannot see it. There is nothing to see. Historians call that style rhetorical algebra, everything in words. The classification comes from a German Orientalist named Georg Heinrich Ferdinand Nesselmann, who in 1842 published a study of Greek algebra in which he proposed 3 stages. Rhetorical, where everything is written out longhand. Syncopated, where you start using standard abbreviations, the way Diophantus of Alexandria did around the middle of the 3rd century, shortening the Greek word isos, meaning equal, to a couple of letters. And symbolic, where you have a full working language of signs and the words drop away entirely. That scheme is in every textbook. It is neat, it is progressive, it looks like evolution, and I want to flag right now that a serious body of modern scholarship thinks it is wrong. We will come back to that, because the objection is a good one, and it complicates everything I am about to say, but take the surface of it first, because the surface is real even if the ladder is not. For most of recorded mathematical history, an equation was a paragraph. Think about what that does to a working brain. You are trying to manipulate a relationship between quantities. In symbols, the relationship is a spatial object. It sits still on the page. You can see the whole of it at once, you can see which parts balance, and you can perform an operation on it by physically moving marks from one side of a line to the other. The page holds the state for you. Your working memory is freed to do the one thing it is actually good at, which is noticing. In prose, there is no page object. The relationship exists only as a sequence you are holding in your head while you read forward through a paragraph. By the time you reach the end of the sentence, the beginning of it is fading. You cannot see both sides at once, because there are no sides. There is only a stream of clauses. That is not a soft literary point. That is a hard constraint on the machinery. And it gets worse the further you go, because the thing about mathematics is that it does not stay at 1 square and 10 roots. Take the year 1540, 512 years before Recorde. In Nuremberg, a book appears called Ars Magna, The Great Art, by Girolamo Cardano, and it contains something genuinely new in the history of the world, which is a general method for solving cubic equations. This is one of the great results of Renaissance mathematics. It broke a problem that had been open since antiquity. And it is written entirely in words. There is no symbolic manipulation in it worth the name. Cardano has to describe each case of the cubic separately, because without a sign for the negative he cannot treat them as one equation with coefficients that might go either way. He ends up with something like 13 distinct cases where we have one. 13 separate theorems, each with its own prose procedure, all of them describing what we now write as a single line. And the method did not even originate with him. He got it under an oath of secrecy that he then broke from Niccolo Tartaglia, who had worked out the solution to one family of cubics, and who communicated it to Cardano in the form of a poem. An actual poem, in Italian in verse, 25 lines of it, rhymed so that it could be memorized. When the cube and the things together are equal to some discrete number, find 2 others that differ in this one. That is what a formula looked like in 1539. It looked like a poem, because a poem is a technology for holding a sequence in a human head, and human heads were the only place a procedure could live. Stop for a second on the sheer weight of that. Tartaglia solved the cubic. It was, at the time, arguably the hardest thing any European had done with numbers in 1,000 years. And in order to transmit it to another mathematician, in writing, on paper, the best available format was rhyming verse. Now put that beside Recorde's 14 roots plus 15 equals 71, and the 4 seconds it takes you to solve it. Here is the claim that this whole story is usually mobilized to support, and I want to state it in its strongest form before I start attacking it. The claim is that notation is not a recording system. It is a cognitive prosthesis. It does not write down thoughts you already had. It makes thoughts available that were not available before. And on that view, the 5,000 years of mathematics before symbolic algebra were not 5,000 years of people being slower than us. They were 5,000 years of people being unable to reach a shelf we can reach without stretching, because somebody eventually built a ladder and left it there, and we grew up assuming the ladder was part of the room. If that is true, and I think some version of it is true, then a very unpleasant corollary follows, and it is going to sit under this entire script like a stone in a shoe. You did not think your way to the shelf. You inherited the ladder. And nobody has ever checked whether the ladder reaches everywhere, or whether there are whole regions of the room that are dark, because the notation for them was never invented, and there is no way from inside the room to find out. Hold that. I will not come back to it for a while, because the honest version of this story requires me to tell you that a lot of serious historians think the ladder metaphor is a lie we tell ourselves backwards. The most forceful of them is a scholar named Netz, whose book The Shaping of Deduction in Greek Mathematics came out of Cambridge in 1999 with the subtitle A Study in Cognitive History. Netz's argument is that the Greeks were not sitting around waiting for algebra. They had a symbolic technology of their own, and it was the lettered diagram. The figure with points labelled alpha, beta, gamma, and a rigid, formulaic verbal apparatus that referred to those letters. Netz's point is that this combination did exactly what notation does. It fixed reference. It let you talk about a specific object without ambiguity. It offloaded the relationship onto the page. The Greeks did not lack a symbolic system. They had a different one, tuned to geometry rather than to quantity, and it carried enough weight to produce Euclid and Archimedes and Apollonius, which is not a record you dismiss. There is a similar objection from Jens Heurup on the Babylonian material, which turns out to be far more structurally sophisticated than the word problems make it look, and a much sharper one from Albrecht Hafer, who has written directly against Nesselmann's 3 stages under the title The Myth of Syncopated Algebra. Hafer's case is that the ladder is a normative fiction constructed in the 19th century by people who already knew what the top rung looked like, and then went looking for the bottom ones. The real historical record is patchy, non-linear, and full of people doing recognisably symbolic reasoning centuries before they had the symbols, and people with excellent symbols doing very little with them. I take that seriously. It is the strongest counter-argument in the field, and it deserves more than a nod. But it does not dispose of the problem. It relocates it. Because even if you grant every word of it, you still have to explain the 100 years. Between roughly 1630 and 1730. In the window during which symbolic notation finally stabilised into something like its modern form, European mathematics produced analytic geometry, the theory of probability, logarithmic computation at scale, the differential and integral calculus, the calculus of variations, and the mathematical description of gravitation. In 1 century, after 5,000 years in which the rate of production was, by comparison, nearly flat. You can argue about causation. You cannot argue about the shape of the curve. Therefore, the real question is not whether notation matters. Nobody who has looked at that curve thinks notation does not matter. The question is, what kind of thing notation is, and what it is doing to the person using it, and whether the person using it can tell. And the strangest way into that question, the way I did not expect when I started reading, runs through a prison cell in Southwark. Robert Recorde was born in Tenby, on the Pembrokeshire coast in southwest Wales, around the year 1510. I say around because nobody knows. The Dictionary of National Biography and most of the older reference works give circa 1510. The Dictionary of Welsh Biography and several modern accounts give circa 1512. There is no baptismal record. The man who gave the world its symbol for exact correspondence has a birth year that historians cannot pin to within 2 years. His father Thomas was a merchant, the son of a Roger Recorde who had set the family business up in the town. His mother was Rose, daughter of Thomas ap John of Machynlleth. Tenby in the 1520s was a walled port town of a few thousand people, trading wine and cloth and fish across the Bristol Channel, and it was the kind of place a bright second son left. He went up to Oxford at about 15. In 1531 he was elected a Fellow of All Souls, which is not a place they hand fellowships out casually then or now. Then he moved to Cambridge and took a doctorate in medicine in 1545. He taught mathematics at both universities. He practiced medicine in London. There is a tradition, hard to document but repeated in every account, that he served as physician to Edward VI and then to Mary. That is an unremarkable and rather glittering career, and if it had continued in that shape, he would be a footnote in the history of Tudor medicine. But in January of 1549, he took a government post, and the government post is what killed him. He was made comptroller of the Bristol Mint. This was the reign of Edward VI, the boy king, and English coinage was in a state that modern economists would describe with some enthusiasm. The Crown had been systematically debasing the currency for years, quietly reducing the silver content of coins while keeping their face value, which is a mechanism for extracting wealth from an entire population without passing a tax. A mint comptroller was the man responsible for the accounts, for checking that what went in matched what came out. He was, in other words, professionally responsible for equality, for the correspondence between two columns. In October of that year, the Western Rebellion was still being suppressed, and the man commanding troops in the southwest was Sir William Herbert. Herbert needed money to pay his soldiers. He wanted it out of the Bristol Mint. Recorde refused. I want to be precise about what that refusal was, because it is the hinge of the whole life. It was not a moral stand against a bad war. It was an accounting objection. The money in the mint was not Herbert's to take, and the ledger would not balance if it left, and Recorde would not sign it out. Herbert had the mint shut down, and had Recorde confined at court for 60 days. 60 days is not a long imprisonment by Tudor standards. It is the kind of punishment designed to communicate, rather than to destroy. And the man delivering it was on his way to becoming the first Earl of Pembroke, a Privy Councillor, and one of the 2 or 3 men who effectively ran England. Recorde did not take the lesson. In May of 1551 he was appointed Surveyor of the Mines and Monies in Ireland. On paper, this was a promotion. In practice, it was a disaster waiting for a name to attach itself to. The job was to run the silver mines at Clonmines in County Wexford, and to oversee the technical side of the Dublin Mint. The Crown had convinced itself there was serious silver in Wexford. It hired a German mining engineer called Joachim Gundelfinger and a company of foreign miners, and it spent an enormous amount of money. There was almost no silver. By June of 1552, a commission had arrived to find out where the funds had gone. The miners were dismissed. The mines closed the following year. Recorde was recalled to England with the failure hanging on him and the accounts of the Irish venture in a condition that nobody has fully untangled since. Here is where a sensible man would have gone quiet, practiced medicine, written textbooks, and died in bed. In 1556, trying to recover his position at court, Recorde formally accused William Herbert, by then the Earl of Pembroke, of malfeasance in his handling of the mints. The charges were probably true. Almost everyone who has looked at the Tudor mint accounts thinks Herbert had his hands in them. That is not the point. The point is that Recorde was a Welsh physician with a failed Irish mining venture behind him, and Herbert was a Privy Councillor who had the complete confidence of Queen Mary and of King Philip of Spain, and Recorde walked into that fight with an accounting argument. Pembroke countersued for libel. The bill was served on the 16th of October, 1556. The hearing took place in Westminster Hall in January of the following year. On the 10th of February, 1557, the court ordered Robert Recorde to pay the Earl of Pembroke £1,000 in damages, plus costs. £1,000 in 1557 is not a fine, it is an erasure, depending on which conversion you trust. You are looking at something on the order of several £100,000 in modern money, and more usefully, you are looking at multiple decades of a professional man's entire income. It was not a sum he could pay. It was not a sum he was ever going to pay. It was a sentence dressed as a number. He was taken to the King's Bench prison in Southwark, and now hold both halves of the year 1557 in your head at the same time, because the coincidence is almost too neat to write down. In February of 1557, Robert Recorde is financially destroyed by a court judgment over a ledger that would not balance. In that same year, 1557, the Whetstone of Witte comes off John Kingston's press in London, containing a new mark, 2 twin lines of one length, invented to say that 2 things correspond exactly, because no 2 things can be more equal. I have gone back and forth on how hard to lean on that. The documentary record does not let me tell you he drew the sign in a cell, and I am not going to invent it. Printing took months. The manuscript was finished before the judgment, and the honest version is that the book and the ruin simply occupy the same 12 months of one man's life. But the man who spent his career insisting that the 2 columns must match, who lost his position for refusing to sign out money that did not belong where it was going, who took on the most dangerous man in England over a set of accounts, is also the man who reached for a symbol of exact correspondence and put it into print in the same year the courts told him his own accounts were worth £1,000 against him. The personal and the technical are not 2 threads here, they are the same thread running in both directions. He made his will in the King's Bench prison on the 28th of June, 1558. It is a modest document. He leaves small bequests to his children, of whom the sources record 4 sons and 5 daughters. He died in that prison in 1558, and nobody knows the day. One tradition gives the 7th of June, which cannot be right if the will is dated the 28th. Several reference works, including the Dictionary of Welsh Biography, state that probate was granted on the 18th of June, 1558, which cannot be right either, because it is 10 days before he wrote the will. There is a transcription error somewhere in the record, and it has never been resolved. The inventor of the equals sign has a death date, a birth date, and a probate date that do not reconcile with each other. 3 numbers in a ledger, and the ledger does not balance. He is buried somewhere in Southwark. Nobody knows where. And then there is the last detail, which is the one that made me put the book down and stare at the wall for a while. The Crown owed Robert Recorde money for his service in Ireland. It had never paid him. The amount, according to the account preserved in the University of St Andrews History Archive, and repeated in the standard biographical literature, was in the region of £1,000, the same figure. Give or take, the exact sum that destroyed him was the exact sum the state already owed him and had simply not handed over. He died in a debtor's prison as a creditor of the government that imprisoned him. The Crown paid it. In 1570, 12 years after he was dead. There is a version of this story where that is a tragedy and you feel appropriately sad, and we move on to the mathematics. I do not think that is what it is. I think it is a structural fact about how institutions handle people who insist on correspondence, and I think it explains something about what happened to his symbol over the following century, which is that nothing happened to it at all. Because there is one more piece of the biography that everyone leaves out, and it is the piece that should genuinely annoy you. Recorde was not a marginal figure in English publishing. The ground of Artes, his arithmetic, was a hit. The bibliographic study by J.B. Easton, published in the journal ISIS in 1967, counts 47 editions of it, running all the way to its last printing in 1699. 15 of those appeared before the year 1600. That book taught arithmetic to England for 150 years. The Castle of Knowledge, his astronomy book from 1556, was substantial enough that in it he became one of the first writers in English to put the Copernican model in front of an English readership, describing Copernicus as a man of great learning, of much experience, and of wonderful diligence in observation. He does not fully commit to the heliocentric system. He is careful, which, given how the rest of his life went, reads as the one occasion on which he correctly judged which fight to avoid. And the Whetstone of Witte, the book with the sign in it, went through exactly one edition. 1557. That is all. It was never reprinted, not in his lifetime, not in the century after, not ever. The most consequential book in the history of English mathematics was a commercial failure by an author whose other books were bestsellers. Therefore, the symbol did not spread because it was in a popular book. It was in the one book of his that nobody read. 61 years. That is the gap. The Whetstone of Witte, 1557. The next appearance of the equals sign in a printed book, 1618. In between, nothing. Not a rival edition, not a citation, not a footnote. Cajori went looking, and Cajori was the most thorough person who has ever looked at this, and what he found in the gap was silence. I want to be careful here, because manuscripts are not print, and there is material that has not been catalogued, and any historian will tell you that absence of evidence in the 16th century is a weak instrument. But the print record is the print record. For 2 full generations, the most successful symbol ever devised by a human being sat in one unsold English book and did nothing. The reasons are not mysterious once you look at them, and they are all depressingly mundane. The first is language. Recorde wrote in English on purpose. It was the great project of his life, putting mathematics into the vernacular so that merchants and surveyors and ordinary literate people could use it. It is genuinely admirable, and it was, for this specific purpose, fatal. Mathematics in the 16th century was conducted in Latin. A German cosist and an Italian algebraist and a French analyst could all read each other because they were all writing in the same dead language. English was a provincial dialect spoken on a damp island by people the continent did not consider serious. Nobody in Bologna or Nuremberg or Paris was going to pick up a book written in the language of Recorde's Whetstone, and almost nobody could have read it if they had. The second is that the book failed commercially. 1 edition, no reprints. It was not sitting on shelves waiting to be rediscovered. It was scarce, almost immediately. The third is that Recorde died the following year, in prison, in disgrace, with a libel judgment against him. There was no author to promote the second edition, and there was a reason for a publisher not to want one. And the fourth reason is the one I keep coming back to, because it is the one that generalizes. There was no mechanism. There is no committee that adopts mathematical notation. There never has been. There is no standards body, no vote, no authority. A symbol spreads because one person reads it, likes it, uses it, and someone else copies them. It is a purely mimetic process running on personal contact and available texts. And in 1558, the person who might have carried it forward was dead, and the text was out of print. And this is where I want to pay off something I left hanging near the start, because it has been sitting in the back of this whole story, and it is the only explanation I have found that actually fits the timing. The question was why the equals sign appears twice, independently, in the middle of the 16th century, when nobody had wanted one for 5,000 years. Recorde in London in 1557. An anonymous hand in Bologna, somewhere in the same window. 2 people, no contact, same mark, same decade, after 50 centuries of nothing. I think the answer is the printing press, and I think it works for a reason that is not the obvious one. The obvious answer is that printing spread ideas faster, and that is true, and it is not the point. The point is what printing does to a symbol. In a manuscript culture, an abbreviation is a private convenience. A scribe develops a shorthand, uses it through one document, and the shorthand dies with the document, or survives in a handful of copies made by hand, each of which may render it slightly differently or not at all. There is no reason to invest in a good symbol, because a symbol only becomes valuable when it is stable across copies, and manuscripts are not stable across copies. They are the opposite of stable across copies. The whole business of medieval textual scholarship exists because they are not. Movable type changes what a mark is. A printed sign is identical in every copy of the edition, and identical in the next edition, and identical in a book printed in another city by a printer who has never seen the first one. For the first time in history, a mark could be a fixed public object rather than a personal habit. And that changes the economics of inventing one. In a manuscript world, inventing a good symbol buys you almost nothing, because it will not propagate. In a print world, inventing a good symbol is potentially the most leveraged act available to a writer, because if it takes permanently and identically everywhere. Recorde was writing for a printer. He says so in the passage itself. He says he will set the mark as he does often in his working use, meaning he already used it privately, in his own manuscripts, for his own convenience. The invention was not the mark. The invention was the decision to put a private convenience into type, where it would come out the same in every copy. The other side of this is a constraint that I find delightful and that almost nobody mentions. A printed symbol has to physically exist in a case of type. It has to be cut in metal by a punch cutter, or improvised from something that is already in the case. Recorde's original sign is long, much longer than the modern one, and the most likely reason is that it was set from two pieces of printer's rule, the plain lengths of metal used for drawing lines across a page, because those were sitting there and a purpose-cut equal sign was not. Descartes' looped mark had a similar advantage on the continent, because the joined A and E already existed in every Latin printing house on the planet, which means that the shape of the symbol at the centre of all formal reasoning was constrained, in part, by what was already lying in a wooden tray in a print shop, which means the survival of the equal sign was not a matter of merit. It was a matter of transmission. And transmission in the 16th century meant a specific individual physically holding a specific copy of a specific rare book. The book that carried it forward, when it finally came, is a footnote to a footnote. In 1618, an English translation appeared of John Napier's Descriptio, the book that introduced logarithms. The translator was Edward Wright, who had died in 1615, so the edition was seen through the press by others. Appended to it was an anonymous set of tables and notes. That appendix contains an equal sign. The appendix is unsigned, and the consensus of the historians who have looked at it is that it was almost certainly written by William Orchard. 61 years of silence, and the sign comes back in an unsigned appendix to a translation of somebody else's book by a man who had been dead for 3 years. Nobody noticed. There is no contemporary remark about it. It just sits there. But 1618 is the crack, and 13 years later, the door comes off its hinges, because in the single year 1631, 3 separate English books appear using Recorde's sign, and after that, it never disappears again. The first is Richard Norwood's Trigonometria, which matters least, and which I mention for completeness. The second is William Orchard's Clavis Mathematicae, the key to mathematics, which was the most influential English mathematics textbook of the 17th century, and which taught the sign to a generation that included John Wallis and Christopher Wren. The third is Thomas Harriot's Artis Analytica Praxis, and the third one is where this stops being a story about notation and becomes a story about who gets to decide what a dead man meant. Thomas Harriot is one of the strangest careers in the history of English science, and the fact that you have probably never heard of him is itself part of the pattern I keep running into in this material. He was born around 1560. He went to Oxford. He was hired by Sir Walter Raleigh as a mathematician and navigational expert, and in 1585 Raleigh sent him across the Atlantic with the expedition to Roanoke Island, off what is now North Carolina. Harriot spent about a year there. He learned enough of the Algonquian language to compile a phonetic alphabet for it. He wrote the account that was published in 1588 as a brief and true report of the newfound land of Virginia, which is one of the earliest English descriptions of North America and which is still read by historians of the period. That is already more than a normal career holds. It is not the interesting part. On the 26th of July, 1609, Thomas Harriot pointed a telescope at the moon from a house in England and drew what he saw. That drawing survives. It predates Galileo's published lunar observations. Harriot was, as far as the surviving record goes, the first human being to draw the moon as seen through a telescope. He went on to make hundreds of observations of sunspots and to track Jupiter's satellites. He published none of it. Around 1602, he worked out the sine law of the refraction of light, the relationship that is taught in every physics class in the world under the name of Snell, after Willibrord Snellius, who arrived at it independently more than 15 years later. Harriot had it first. He published none of it. He did substantial work on the algebra of equations, on the structure of roots, on the packing of spheres in response to a question Raleigh asked him about stacking cannonballs, which is a version of a problem that stayed open until the end of the 20th century. He corresponded with Kepler. He was, on the evidence of the papers, one of the 2 or 3 best mathematicians alive. He published none of it, not one page in his entire life on mathematics. Why is a question people have been arguing about for centuries? Some of it looks like temperament. Some of it is almost certainly the political weather. His patron after Raleigh was Henry Percy, the 9th Earl of Northumberland, known as the Wizard Earl, and in 1605 Northumberland was implicated in the Gunpowder Plot and imprisoned in the Tower of London, where he stayed for 16 years. Harriot himself was questioned and briefly held. When your patron is in the Tower for treason, and you are known as the man who does mathematics and looks at the heavens through tubes, there is a decent argument for keeping your papers in a drawer. He died on the 2nd of July, 1621, of a cancer of the nose, which his contemporaries and most modern accounts attribute to the tobacco he had brought back from Virginia and used for the rest of his life. 10 years after his death, a group of his associates, led by Walter Warner, assembled some of his algebraic papers into a printed volume, that is the Artis Analyticae Praxis of 1631. It is the book that put Harriot's algebra into the world, and it did more than almost any other single volume to fix the shape of modern algebraic notation. It contains the equals sign. It also contains the first appearance in print of the symbols for greater than and less than, the 2 arrowheads you have used since primary school. Here is the correction, and it is the kind of thing that once you know it, you cannot stop seeing. Harriot did not use the equal sign. In his own surviving manuscripts, in his own hand, equality is written as 2 short vertical bars. Not horizontal. Vertical, a different mark entirely, from a different tradition. The equal sign in the praxis was put there by the editors 10 years after Harriot was dead, because by 1631 that was the sign that Orchard and the English school were using, and it was the sign the printer could set. The greater than and less than symbols are Harriot's, those he did invent. The equality sign in the book that made him famous for notation is not his. It is Walter Warner's editorial decision about how to render a dead man's handwriting. I would like you to sit with the shape of that for a second, because it is going to keep happening. The 3 books that saved the equals sign are an anonymous appendix, a textbook by a country parson, and a posthumous edition assembled by a man whose name has vanished from the record. Not one of the people who actually put the sign into general circulation invented it. The person who invented it had been dead for 74 years and was buried in an unmarked grave in a debtor's prison, and if you had asked any English mathematician in 1631 where the symbol came from, I am not confident more than a handful could have told you. That is the mechanism, not genius recognized, not merit rising. A rare book, a translator's appendix, a schoolmaster's habit, and an editor tidying up a manuscript for the press. There is something I want to say about how you are able to hear all of this for the first time, at your age, having been through whatever mathematical education you were put through. You can complete a full degree in mathematics at almost any university in the world and never once be told where a single symbol came from. Not one lecture. Not one slide. The plus sign. The minus sign. The equal sign. The integral. The letter X for the unknown. The arrowheads for inequality. The raised number for a power. You will use all of them thousands of times for years, and at no point will anyone mention that they were invented by people with names for reasons, and that the reasons were frequently trivial and occasionally commercial. The history of mathematical notation is not part of mathematics. It sits in history departments, when it sits anywhere. And it is small and underfunded, and read by a few dozen specialists. Cajori's 2 volumes, which are the foundation of everything I have told you, and which represent decades of one man's life spent in rare book rooms, are the sort of thing you find as a scanned image on an archive site because the print runs ran out. I do not think this is a conspiracy, and I want to be careful not to imply that it is. It is something more ordinary and in a way more annoying. It is a curriculum decision, repeated across every institution independently, that the history is not load-bearing, that you can learn the tool without learning that it is a tool. But look at what that produces. It produces practitioners of the most notation-dependent discipline in the whole of human knowledge who have never been given a reason to see the notation as a set of choices, who experience the symbols as part of the subject rather than as a layer laid over it by specific people in specific centuries who could have done otherwise, who cannot therefore ask the question of whether the layer is any good, because you cannot evaluate something you have never seen the edges of. Voevodsky had to arrive at the question the hard way, through a false theorem of his own that stood for 15 years, because nothing in his education had suggested that the equals sign was the sort of thing you were allowed to have a problem with. That is the invisible part of this. Not that anyone hid it. That it was never considered worth mentioning, and so an entire profession inherited a set of 400-year-old decisions made by a Welsh physician with a sore hand and a French philosopher with a printer's ligature, and passed them on for generations as though they had come with the universe. But none of that explains why it won. It only explains how it survived, and it did not survive into an empty field. Because by the time Orchard and Warner were putting Recorde's twin lines into English print, a different symbol was about to appear in France, in the most famous book of the century, under the name of the most famous thinker in Europe, and for the next 60 years. The question of how a European mathematician wrote the word equals was genuinely, openly undecided. Cajori, writing in 1928, put it in a sentence I have not been able to shake. Recorde's symbol, he said, had several competitors, and it nearly perished in its fierce struggle for existence. That is a historian of mathematical notation, using the language of natural selection. And he meant it. He had spent decades cataloguing signs, and what he found was not a story of good ideas being recognised. It was a story of variants competing for hosts. Let me show you the field. The first and largest competitor was the one that had been winning for 5,000 years, which was to write the word, equales, equantur, faciunt, meaning they make, in German, gleich, in Dutch, gelijk, or the abbreviation ek, or the tied letters A and E run together into the single character that Latin printers already had in their cases. That was the default, that was what everybody understood, and there was no obvious reason to abandon it. When Michael Stiefel published the Arithmetica Integra in 1544, which is the most important German algebra book of the century, and which Recorde had certainly read, Stifel had a full apparatus of Cossack symbols for the unknown and its powers, and he wrote equality out as a word. Christoph Rudolph, in the Kos of 1525, the same. Those are not primitive books. Stifel is doing serious work on negative numbers and on the relationship between arithmetic and geometric progressions that points directly at logarithms. He had every technical reason to want a compact sign, and he did not reach for one. The second competitor is older than all of it. Diophantus of Alexandria, working around the middle of the 3rd century of the Common Era, wrote the Arithmetica, and in it he used a compressed form of the Greek word isos, meaning equal, as a marker in his equations. This is the thing people mean when they say the Greeks had an equal sign. They did not. An abbreviation of a word is not a symbol. It is a shorter word. It carries the same conceptual load as the word, it points back to the spoken language, and it does not become an object you can manipulate. Diophantus is doing something clever, and it is not the same operation Recorde performed. The third competitor came out of Diophantus. In 1575, in Basel, a German scholar named Wilhelm Holtzmann, who wrote under the Hellenist name Xylander, published the first proper Latin edition of Diophantus, and in it, to render equality, he used 2 vertical bars, side by side. 2 parallel lines, exactly like Recorde's, rotated 90 degrees. Moritz Cantor's suggestion is that they came from a doubled Greek iota, standing for isoi. You will find sources, including some very widely read ones, dating this to 1571. That is wrong. 1571 is the year of Xylander's translation of Strabo. The Diophantus is 1575. It is a small thing, but it propagates, and it is a reminder of how much of what circulates about this subject is copied rather than checked. The point of Xylander is that 2 parallel lines occurred to someone else, independently, 18 years after Recorde, and they chose to stand them upright. Harriot, working in England 40 years later, used the upright version too. There was nothing inevitable about the horizontal. The fourth competitor is the strangest, and I have a soft spot for it. In 1634, in Paris, the first volumes appeared of a 6-volume Cursus Mathematicus by a man publishing as Pierre Herigoni, which was in all likelihood a pseudonym. Herigoni was building a completely symbolic mathematics, an attempt to write out the whole of Euclid in signs with no natural language at all, which is a genuinely radical project and about 250 years early. For equality, he used a 2, a vertical stroke, and another 2. For inequality, he used a 2 and a 3, with the smaller digit on the side of the smaller quantity, which is an elegant piece of design and which nobody adopted. Herigoni's system is better than the one you use in several specific respects, and it died completely. That happens more often than the tidy history admits. And then, in 1637, the real one arrives. René Descartes publishes the Discourse on Method, and appended to it, as one of 3 essays demonstrating the method in action, is La Géométrie. It is one of the most consequential mathematical texts ever written. It fuses algebra and geometry into a single subject. It gives you the convention, which you still use and have never once questioned, that letters from the end of the alphabet stand for unknowns, and letters from the beginning stand for knowns, which is why the unknown in every equation you have ever solved is called x. It gives you the raised exponent for powers. Most of what an algebraic expression looks like on a page, you are looking at Descartes. And for equality, he used a mark that looks like a lowercase letter tipped onto its back and reversed, a small open loop with a tail. It is generally taken to be a distortion of the joined A and E of equalis, worn down through handwriting into a single stroke. That symbol is the one that nearly won. I want to correct something here because this is where the popular version of the story goes badly wrong. People say Descartes invented modern algebraic notation. He did not invent modern algebraic notation. He invented most of it and then chose the wrong sign for the single most common relation in the subject. And the thing you actually write is a compromise between Descartes and a Welshman who had been dead for 80 years when the geometry was printed. The notation in your head has two fathers, and they never met, and they would not have agreed. Why did Descartes' mark nearly win? Not because it was better. On the merits, it is worse in three separate ways. It is asymmetric, which is exactly wrong for a symmetric relation. It is harder to set cleanly in type. And it looks like several other things that were already in use. It nearly won because of distribution. La Géométrie was published in French, which was a problem for its continental readership. So in 1649, a Dutch mathematician named Frans van Schooten the Younger produced a Latin edition. And then in 1659 and 1661, he produced a vastly expanded second edition in 2 volumes, with commentary, with worked examples, with contributions from his own students. And his students were Johan Huddy, Hendrik van Heuraet, Johan de Witte, and Christiaan Huygens. That is not a publishing operation. That is the entire front line of European mathematics in one house in Leiden. Van Schooten's Geometria is the book that taught Newton his analytic geometry. It is the book that carried Descartes' method across the continent and into England, and every page of it used Descartes' equality symbol. By 1660, if you were a serious working mathematician anywhere between Amsterdam and Bologna, the odds were good that the book you had learned from used the looped mark, and that Recorde's 2 lines looked to you like an English provincialism. Cajori's judgment, and he had read more of the primary material than anyone before or since, is that the outcome came down substantially to geography, where you were determined which symbol you inherited: proximity to Descartes, proximity to Leiden, proximity to Oxford, and when the 2 systems collided, the tie was broken not by argument, but by the prestige of whoever the reader happened to respect. In the end, the decisive figure was Leibniz, who chose the 2 lines. And Leibniz was the most influential notational thinker who has ever lived, and after him the question was closed. Stop for a moment on that, because I think it is the most important paragraph in this entire story, and it is buried in a technical monograph nobody reads. The equals sign did not win because it was clearer. It did not win because a community of experts evaluated the alternatives and selected the best one. There was no evaluation. There was no community that could have performed one. It won because a specific rare English book reached a specific schoolmaster, whose textbook reached a specific generation of English mathematicians, whose work reached Leibniz, who liked it. Now run the counterfactual, and run it honestly, because it is not far-fetched. Van Schooten's edition of 1659 is the standard text for the generation that includes Newton. Suppose Ortrud had died in 1620 before writing the Clavis. Suppose Warner had rendered Harriot's vertical bars as vertical bars, which is what they actually were. Suppose the Napier Appendix of 1618 had used the word, like everyone else. There is then no English school of the 2 lines for Leibniz to encounter. There is only the Cartesian mark, in the best book on the continent, taught to everyone who matters. You would be writing equality as a small backward loop right now. Every equation on every blackboard on Earth would look different. And nothing whatsoever about mathematics would have changed, except that you would think the loop was obvious and natural, and that 2 horizontal lines would look strange to you. That is the part I cannot get past, and it opens the second layer of this whole thing. Because if the symbol you use for the deepest relation in all of formal thought is the survivor of a mimetic accident, decided by book distribution and personal prestige between 1630 and 1660, then the specific shape of your mathematical thinking is contingent in a way you have never had reason to consider. And a much worse question follows from that, and I'm going to put it in front of you now and then leave it alone for a long time. The competition was between symbols that got invented. Recorde's lines beat Descartes' loop, and Xylander's uprights, and Herigoni's numerals, and the plain Latin word. Fine, somebody won. But every one of those was a proposal for the same idea. All of them were trying to write equals. The competition was never between different ideas about what relation deserved a symbol. It was a beauty contest between candidates for a job that had already been defined. What happened to the relations that nobody proposed a symbol for? There is no record of those. There cannot be. A notation that was never invented leaves no trace, and the thoughts that would have required it leave no trace either, because they were never had. The history of mathematical notation is a history of what got written down. It is silent, structurally and permanently silent, about what could not be. Hold that. We are going to come back to it, and when we do it will not be about mathematics. Gottfried Wilhelm Leibniz is the person who understood this before anyone else, and he understood it so completely that his life's ambition looks, from the outside, like the ambition of a crank. He wanted to build a universal notation, not for mathematics, for everything. He called it the Characteristica Universalis, the universal character. The idea was a system of signs in which every concept, including moral and legal and metaphysical concepts, would be assigned a symbol composed out of the symbols for its parts, so that the structure of the symbol would mirror the structure of the idea, and then, alongside it, a calculus ratiocinator, a reasoning calculus, a set of rules for manipulating those symbols such that valid inference became a mechanical operation. His famous line about it is that if this were built, then when two philosophers disagreed they would not need to argue. They would take up their pens, sit down at their slates, and say to each other, "Let us calculate." That sounds like a fantasy of a man who has been staring at a wall too long. It is not. It is a description of what had just happened to mathematics. Generalized, Leibniz had watched a set of marks turn a problem that required a poem into a problem that required 4 seconds. And he asked the obvious follow-up question, which is, how far does this go? He did not manage to build it. Nobody has. But 250 years later, a chain that runs through Boole and Frege and Pinot and Russell and Turing produced formal logic, computability, and the machine you are almost certainly listening to this on. His fantasy is not a failed project. It is the specification document for the 20th century. And in the meantime, he did something much more concrete, which is that he designed the notation for the calculus, and he designed it on purpose, with an explicit theory about what notation is for. In the autumn of 1675, over the course of about a week, Leibniz settled on the 2 marks that every calculus student in the world still uses. He chose a long letter S, stretched out, for the operation of summing, from the Latin summa, that is the integral sign. And he chose the letter D for a difference, from differentia, and he built the derivative as a ratio of 2 of them, d of y over d of x. Now compare that with what Newton did. Newton had the calculus first. He had it by 1666, roughly a decade before Leibniz, and the priority dispute that followed was one of the ugliest fights in the history of science. And Newton's notation for a rate of change was a dot placed above the variable. 1 dot for the first fluxion, 2 dots for the second. The dot is compact. It is elegant. It is fine for what Newton mostly used it for, which was differentiation with respect to time in problems of motion. And it is nearly useless for everything else. Look at what Leibniz's version encodes and Newton's does not. The d of y over d of x tells you, in the shape of the mark itself, which variable you are differentiating with respect to. A dot cannot do that. There is no room in a dot for a second piece of information. which means that the moment you have a function of more than one variable, the Newtonian notation runs out of expressive capacity, and you have to say in words what the Leibnizian notation says in its structure. It gets better. Because Leibniz wrote the derivative as a ratio, the chain rule looks, on the page, like cancelling fractions. It is not cancelling fractions, and mathematicians will correctly tell you not to think of it that way, and every student thinks of it that way anyway, and gets the right answer. Because the notation has been designed so that the manipulation you are tempted to perform is the manipulation that is valid. The symbol is doing the reasoning for you. That is not a happy accident. That is Leibniz, and the integral sign, the long S, sits in front of the expression with a d and a variable at the end of it, so that a change of variable in an integral is a substitution you can perform visually, by swapping marks rather than a step you have to justify from the definition each time. Newton's dots are a way of recording that a rate of change is being taken. Leibniz's marks are a machine for taking it. The British used the dots for 120 years. This is the part of the story that gets told as a straightforward scandal, and I am going to tell it that way first and then complicate it, because the honest version is more interesting than the scandal. The scandal version runs like this. After the priority dispute, British mathematics closed ranks around Newton. The universities, and above all Cambridge, made fluxional notation a matter of national loyalty. The examinations demanded it. Generations of British mathematicians were trained in a notation that could not comfortably express the analysis that was being invented on the continent. And while Euler and the Bernoullis and Lagrange and Laplace built the entire structure of modern analysis in Leibnizian symbols, Britain, the country that had produced Newton, contributed almost nothing to the subject for a century. Then, in 1812, 3 Cambridge undergraduates founded what they called the Analytical Society for the specific purpose of importing continental notation. One of them was John Herschel, one was George Peacock, and one was Charles Babbage, who would later spend his life trying to build a mechanical computer, which is not unrelated. Babbage described their program as the principles of pure D-ism, as opposed to the dot age of the university, which is a joke about the letter D, a joke about dots, and a joke about senility, all at once. And which tells you exactly how much contempt these young men had for what they had been taught. They translated a French textbook by Recorde in 1816. Peacock got Leibnizian symbols into the Cambridge examination papers in 1817, and British mathematics started moving again. That is the version you will read almost everywhere, and it is roughly true. Here is where I have to be careful. Historians who work on 18th century British mathematics push back on the strong form of this claim, and they have a case. Colin Maclaurin was not an idiot. Brooke Taylor gave us Taylor series. Abraham de Moivre did foundational work in probability and complex numbers. James Stirling has a formula named after him that every physicist uses. The dot notation did not physically prevent good mathematics, and the reasons for the British lag are also institutional, cultural, and financial, having to do with how the universities were funded, what they were for, and the near total absence of anything resembling a research career. So notation was not the only cause. I think the strong claim is overstated, but I also think the weak claim is undeniable, and the weak claim is bad enough. 2 communities of intelligent people, with equal access to the same underlying ideas, given different sets of marks to think with, diverged sharply in productivity over a century, and the community that recovered did so by explicitly and deliberately changing its marks. That is close to a controlled experiment, and it comes out the way you would expect. The other thing that strikes me, and I have not seen it made much of, is what the Analytical Society actually did. 3 students at Cambridge in 1812 looked at their own education and concluded that the problem was not that they were being taught the wrong facts. The problem was that they were being taught the wrong symbols. That is an unusual diagnosis for a 19-year-old to make. It requires you to notice the thing you are looking through rather than the thing you are looking at. Almost nobody does that about anything once in their lives. The best statement of the underlying principle comes about a century later, from a mathematician who was also a serious philosopher, and it is worth hearing in his own words because he says it more sharply than anyone since. Alfred North Whitehead, in an Introduction to Mathematics, published in 1911, wrote this: "It is a profoundly erroneous truism, repeated by all copybooks and by eminent people when they are making speeches, that we should cultivate the habit of thinking of what we are doing. The precise opposite is the case. Civilization advances by extending the number of important operations which we can perform without thinking about them. Then he adds the image that makes it land. Operations of thought, he says, are like cavalry charges in a battle. They are strictly limited in number, they require fresh horses, and they must only be made at decisive moments." Elsewhere in the same book he puts it even more bluntly, and says that the use of a calculus is, after all, nothing but a way of avoiding reasoning. That is the thesis in one line. A good symbol is not a way of expressing a thought, it is a way of not having to have one. Now, is that just an elegant metaphor from an Edwardian mathematician, or is there something underneath it? There is something underneath it, and the something has been measured. In 1956, George Miller published a paper in the Psychological Review with the title The Magical Number 7, Plus or Minus 2, and it is one of the most cited papers in the history of psychology. The finding, in the crudest possible summary, is that the number of distinct items a person can hold in immediate memory at once is small. Around 7, and later work suggests the real figure for pure working memory is closer to 4. That is the entire capacity of the workspace in which you consciously manipulate anything. 4 items. That is the whole desk. Miller's other contribution, and the one that matters here, is the idea of chunking. The capacity limit is not on information, it is on chunks. If you recode a string of items into a single unit, that unit costs you 1 slot regardless of how much is packed inside it. A phone number is a dozen digits, or it is 3 chunks, depending entirely on how it has been written. An algebraic expression is a chunking device. When you look at a quadratic, you do not hold 6 separate quantities and their relations in working memory. You hold one object, with a shape, and the shape tells you what you can do to it. The page holds the parts. Your 4 slots hold the whole. That is what al-Khwarizmi did not have. He had the same 4 slots you do. He was working on the same hardware. He simply had no way to compress, and so every step of a derivation had to be carried as a sequence, in language, in time, with the earlier parts decaying while the later parts arrived. The formalization of this in education research is John Sweller's cognitive load theory, which starts from exactly this premise. That working memory is the bottleneck in all learning, and that the design of the material determines how much of that bottleneck is wasted on the format rather than spent on the content. Rewrite a problem badly, and you can make it unsolvable for a person who could solve it easily in a better layout, without changing the mathematics at all. And then there is the philosophical version, which goes further than I am entirely comfortable with, and which I think is probably right anyway. In 1995, Edwin Hutchins published Cognition in the Wild, a study based on years of observing navigation aboard a United States Navy ship. His conclusion was that the computation which brings a ship into harbour is not happening inside any individual head. It is distributed across a set of people, a set of instruments, a chart, a set of procedures, and the physical layout of the bridge. No one person on that bridge knows the ship's position. The system knows it. The cognition is in the arrangement. 3 years later, in 1998, Andy Clark and David Chalmers published a short paper in the journal Analysis called The Extended Mind, and it is one of those papers that is either obviously true or obviously absurd, depending on the hour of the day. Their argument is that if an external object is reliably available, automatically consulted, and trusted, then there is no principled reason to draw the boundary of the mind at the skull. A notebook that a person with memory impairment consults constantly is functioning as memory. Not like memory, as memory. Apply that to notation, and you get a conclusion that I find genuinely difficult. When you solve an equation on paper, the paper is not a record of your thinking. It is part of the thinking. The marks are holding state that your head cannot hold. The spatial arrangement is performing inference that you are not performing. When you move a term across the equals sign and flip its sign, you are not reasoning about the additive inverse. You are executing a rule about mark positions, and the rule was designed by somebody else, centuries ago, to give the right answer without your involvement. You are not doing the mathematics. You are running it. And the thing you are running it on was assembled by a small number of dead men, none of whom were designing for you, most of whom were solving a local problem, one of whom was simply tired of writing a phrase. Which brings me to the thing that I did not expect to find, and which has changed how I look at the mark entirely. Robert Recorde's symbol 1. It is now, by a wide margin, the most frequently written symbol in the history of the species. It appears in every physics paper, every set of accounts, every spreadsheet cell, every line of code, on the keyboard in front of you, in the Unicode standard, on the calculator in your pocket. And the idea it was invented to express has, in the general population, largely lost. Here is what I mean. Recorde's sign asserts a relation. It says that the thing on the left and the thing on the right are the same quantity, described two different ways. It is symmetric. It is static. It makes a claim about the world, and the claim is either true or it is not. And you can read it in either direction because the relation does not have a preferred direction. That is what mathematicians call the relational understanding of the equals sign. Now think about what it meant to you when you were 7. It meant, do the sum. It meant the answer goes here. 2 plus 3 equals, and then there is a box. And you write 5 in the box. The sign is not a claim about correspondence. It is an instruction. It is the point in the sentence where the machinery produces its output. It has a direction, left to right, and the right-hand side is where the answers live. That is the operational understanding, and it is not a childish error that people grow out of. It is a stable, measurable, persistent misreading that a large fraction of the population carries for life. The research on this is unambiguous, and it is genuinely uncomfortable reading. In 2006, Eric Knuth, Anna Stevens, Nicole McNeil and Martha Alibali published a study in the Journal for Research in Mathematics Education, looking at what middle school students actually think the sign means. Depending on the grade, somewhere between 32 and 52% of 6th and 7th graders gave a relational definition, which means that roughly half to 2/3 of them, at 11 and 12 years old, after 5 or 6 years of daily use, did not think the symbol meant that two things are the same. A later study by Emily Fife and colleagues looked at a wider age range and found that around 62% of students from 7th grade to 12th grade gave a relational answer. Which is better? It also means that nearly 2 out of 5 students, some of them about to leave school, some of them about to take university mathematics, still read the most common symbol in the subject as an instruction to compute. And you can see the consequences directly in what those students will and will not accept. Show a student with the operational reading the statement that 8 is equal to 8, and a significant number of them will reject it, or call it strange, because there is no operation on the left, and if there is no operation there is nothing for the sign to do. Show them 9 equals 5 plus 4, and they will tell you it is written backwards. The answer is on the wrong side. There is not supposed to be a sum after the sign. Those students are not confused about arithmetic. They can add. They are confused about the symbol, and the confusion tracks directly into their ability to do algebra, because algebra is nothing but the manipulation of a symmetric relation, and if you think the relation has a direction, then every step you take is a step you do not really understand. There is a study by Matthew and Lynn Fuchs and colleagues finding that a student's understanding of the equals sign at the end of 2nd grade predicts their algebra competence 2 years later, not their arithmetic ability, their understanding of 1 mark. And when the same research group went looking for the source of the misreading, they found it in the books. A study by Nicole McNeil and colleagues in Cognition and Instruction, also from 2006, analysed the middle school textbook series being used in American classrooms and found that the sign was presented overwhelmingly in the operations equals answer format, and only rarely in contexts with operations on both sides. The books were teaching the misconception, not through error, through layout, through the sheer repetition of a visual pattern in which the sum is always on the left and the answer is always on the right. 469 years after a man wrote that he chose 2 twin lines because no 2 things can be more equal, the majority of people who use his mark every day of their lives do not read it as a statement about 2 things being the same. They read it as a button. That should bother you more than it probably does. We did not fail to teach people the symbol. The symbol is universal. We taught them the symbol and failed to transmit the idea, which suggests that the marks and the meanings can come apart, and that a notation can propagate perfectly while the thought it was built to carry quietly does not. And then it got worse, and it got worse on purpose, and we know exactly who did it and when. In the middle of the 1950s, a team at International Business Machines led by John Backus was designing the first widely used high-level programming language. It was called Fortran, from formula translation, and the whole point of it was to let a scientist write something that looked like mathematics and have the machine turn it into instructions. The language was specified across 1954 to 1956, and the first compiler was delivered in 1957. 400 years almost exactly after the Whetstone of Witte. And in Fortran, the equals sign does not mean equals, it means store. When you write that x equals 2 in that language, you are not asserting anything, you are issuing a command. Take the value 2 and put it in the memory location named x, destroying whatever was there before. The sign is not symmetric. It cannot be read backwards. It has an actor and a target. And the moment you have that, you can write the line that would have made Recorde put down his pen, which is x equals x plus 1, as a mathematical statement that is false for every value of x. There is no number that is 1 greater than itself. As a line of code, it is one of the most common instructions ever written, executed uncountable trillions of times a day in every running program on Earth. And it means take what is in x, add 1, and put the result back. The sign for perfect correspondence had been reassigned to mean overwrite this. The reason is banal, which is somehow worse. Early computer character sets were tiny. The available symbols were whatever the key punch could produce, and there was one obvious character sitting there for a relation between 2 quantities. And Backus's team took it. Testing for actual equality got shunted off into a 3-character code: a dot, the letters E and Q, another dot, because that was what was left. It did not have to go that way. In 1958, and then in 1960, the International Committee designing alcohol looked at exactly this choice and refused it. They used a colon followed by an equal sign for assignment and reserved the plain sign for equality, on the entirely reasonable grounds that a symbol which has meant one thing for 4 centuries should probably keep meaning it. That convention survives in Pascal, in Ada, in Go's short declaration, in a scattering of languages that are mostly loved by people who care about this sort of thing. And it lost. Because the language that actually conquered the world was C, and C followed Fortran. C used the single sign for assignment and invented the doubled sign for comparison, and every major language descended from it did the same. Java, JavaScript, Python, PHP, Perl, Ruby, C#, Go, Rust, every one of them. So the situation right now, in the notation that more human beings use daily than any mathematical notation in history, is this. 1 line means make this become that. 2 lines means ask whether this is that. And they look almost identical. The result is one of the most famous bug classes in software engineering. A programmer writes a conditional test, means to check whether a value is equal to something, types 1 sign instead of 2, and instead of asking a question, the program performs an assignment, overwrites the variable, and hands back a result that the language happily treats as true. The code compiles, it runs, it gives the wrong answer silently and forever. Generations of defensive programming idioms exist purely to guard against this. Compiler warnings exist purely to catch it. Entire style guides mandate writing comparisons backwards so that the mistake becomes a syntax error rather than a silent catastrophe. All of it downstream of a character set limitation in 1956. And here is the part I find genuinely strange, in the way that keeps you up. Mathematics itself has quietly conceded that Recorde's mark cannot carry the load. Look at what has had to be invented around it. A 3-barred sign for identity, meaning true for all values rather than true for particular ones. A sign with a small triangle or a colon in front of it to mean this is a definition. I am naming this thing, do not check it. A wavy sign for approximately equal. A wavy sign over a straight one for isomorphic. A sign with a dot for congruent. Every one of those exists, because at some point somebody wrote the 2 lines, and it was not clear which of several different claims they were making. Recorde said no 2 things can be more equal. It is a beautiful line. It contains an assumption so deep that it took mathematics 300 years to notice it, and another century to start taking it apart. And the assumption is that being equal is a single thing. Ask a mathematician what equality means, and you will get, depending on who you ask and how tired they are, one of about 4 answers, and they do not agree with each other. The oldest answer is Leibniz's, and it is the one that sounds like it settles the matter. 2 things are identical if everything true of one is true of the other. If there is no property whatsoever that distinguishes them, they are not 2 things. They are one thing with 2 names. That is elegant, and it has a hole in it that you can drive a century of philosophy through, which is that it depends entirely on what counts as a property. Include enough properties, and nothing is ever equal to anything except itself. Include too few, and everything collapses. The 20th century answer, the one that underlies the formal foundation of mathematics as it is normally taught, comes from set theory, and it is brutally simple. 2 sets are equal when they have exactly the same members. That is an axiom. It is called extensionality, and it is one of the first things written down in the Standard Foundation, the system named for Zermelo and Frankel, which is what almost every working mathematician will tell you their subject ultimately rests on. And it produces nonsense. Not in the sense that it is inconsistent, in the sense that it answers questions that should not have answers. In set theory, everything is a set. There are no other objects. which means the number 3 has to be a set, and there is a standard way of building it, due to von Neumann, in which each number is the set of all the numbers below it. 0 is the empty set, 1 is the set containing the empty set, 2 is the set containing those two, and so on upward. That works. It is clean. And it has consequences nobody wants. Under that construction, the number 2 is a member of the number 3. Ask whether 2 is an element of 3, and set theory says yes. Ask whether 2 is a subset of 3, and set theory says yes. Ask whether the number 2 is a subset of the number pi, and the machinery will grind away and produce an answer, and the answer is meaningless. Because that question is not about mathematics. It is about an encoding decision somebody made in the 1920s. Mathematicians call these junk theorems, statements that are formally true, provable from the axioms, and completely without content, because they are artifacts of the representation rather than facts about the objects. Paul Benacerraf wrote the definitive statement of the problem in 1965 in a paper with the title "What Numbers Could Not Be." His argument is that there are many different ways to build the numbers out of sets, that they all work equally well, that they disagree with each other about questions like whether 2 is an element of 3, and that therefore no one of them can be what numbers actually are. If the number 3 were genuinely a particular set, there would be a fact of the matter about which set. There is not. There are only choices. So the foundation of mathematics gives you an equal sign that is too sharp. It distinguishes between things that no mathematician thinks are different, and at the same time, in daily practice, working mathematicians use the sign in a way the foundation does not support at all. Here is what I mean, and it is the single most common informal move in the entire subject. A mathematician will say that 2 groups are the same, or that 2 spaces are the same, when what is literally true is that there is an isomorphism between them, a structure preserving correspondence. Every feature of one matches a feature of the other, and everything you can prove about one, you can prove about the other, and no argument anywhere in mathematics will ever depend on the difference. They are not equal. As sets, they are made of different things. As mathematics, they are indistinguishable. Every mathematician alive treats isomorphic objects as equal, all day, every day, in print. And the formal foundation says they are not, and everybody ignores the foundation, because the foundation is wrong about this and they know it. That gap sat there for most of a century. It was a known embarrassment, the kind of thing you mention in a footnote and move on from, because nothing was going wrong. Human beings could tell which kind of sameness was meant from context, and no one was confused in practice. And then people started trying to get machines to check proofs, and the machines could not tell, because a machine has no context, and the whole thing came apart. Which brings me to Vladimir Voevodsky, and to the second man in this story who spent the end of his life on the meaning of the equals sign and did not live to finish. He was born in Moscow on the 4th of June, 1966, to 2 scientists. He went to Moscow State University and did not graduate. Accounts differ on the details, but the shape is consistent, which is that he refused to attend lectures he considered pointless and failed out. He was publishing serious mathematics at the time. Harvard admitted him to a doctoral program anyway, without an undergraduate degree, on the strength of the papers. He finished in 1992. In 2002, he was awarded the Fields Medal, which is the highest honour in the subject, and which is given only to mathematicians under the age of 40. He got it for constructing a homotopy theory of algebraic varieties, and for proving the Milnor conjecture, which had been open for around 30 years. He went to the Institute for Advanced Study in Princeton, which is where Einstein worked, and he was by any measure at the absolute summit of his field, and then he found the mistake. In the late 1980s and early 90s, Voevodsky and Mikhail Kapranov had published a result about a class of higher dimensional structures called infinity groupoids, claiming that they could serve as models for a certain kind of space. It was a substantial theorem. People built on it. In 1998, a mathematician named Carlos Simpson published a paper containing a counterexample. The theorem was false. Nobody believed him. The paper was, in Voevodsky's own later description, not accepted by the community. Simpson had produced a construction that showed the result could not hold, and the field carried on as though it did, partly because Simpson's paper did not identify the specific error in the original argument, and partly one suspects because of who had written the original argument. It took roughly 15 years for the correction to be absorbed. Voevodsky himself accepted that his own theorem was wrong around 2013. Think about the position that puts a person in. You are one of the best mathematicians in the world. You have the highest prize in your subject. And you have just established, from the inside, that a false result of yours stood in the literature for 15 years, that a correct refutation was published and ignored, and that the entire apparatus of peer review, expert judgment and professional scrutiny did not catch it. Not because anyone was lazy. Because the material is hard, and human beings checking human proofs is a process with an error rate, and nobody knows what the error rate is. Voevodsky's response was not to be more careful. His response was to conclude that the method was broken, and that mathematics needed proofs that machines could verify. And when he went to do that, using the proof assistant software that existed, he ran directly into the equals sign. Because the underlying framework for that kind of computer verification is not set theory. It is type theory, developed largely by the Swedish logician Per Martin Loff from the 1970s onward, and type theory does something with equality that will sound, at first, like a mistake. In type theory, the statement that A equals B is not a claim that is true or false. It is itself a type. An object, a thing with contents, and the contents are the proofs. To say that A equals B is to say that the type of identifications between A and B is inhabited, that there is at least one object sitting in it. And here is the consequence that took decades to be understood properly, and which is one of the strangest facts I have come across in any subject. That type can have more than one element. There can be two different, genuinely distinct, non-interchangeable proofs that A is equal to B, which means that equality is not a yes or no, it is a space. Two things can be equal in more than one way, and the ways can differ from each other, and the difference can carry mathematical information. The picture that makes it intuitive, and which is where the name homotopy type theory comes from, is to think of the objects as points, and the identifications as paths between them. Saying that 2 points are equal is saying that there is a path, and there can be many paths, and paths can be deformed into each other or not, and whether 2 paths can be deformed into each other is itself a question about equality one level up, and that question has its own space of answers, and it goes upward forever. Recorde's twin lines, the flattest and simplest mark in mathematics, 2 straight strokes with nothing inside them, turn out to be sitting on top of an infinite tower. Voevodsky's specific contribution, formulated around 2009, is the univalence axiom, and the crude version of what it says is that equivalence is equality, that 2 mathematical structures which are equivalent, in the precise technical sense, may be identified. It takes the informal move every working mathematician makes 100 times a week and makes it a formal law of the foundation, which means the fix for 4 centuries of imprecision in the most used symbol in mathematics is to stop pretending that the sharp version was ever what anybody meant. He spent the last decade of his life on it. He ran a special year at the Institute in 2012 and 13 that produced a book with about 50 authors, written collaboratively and released free, because he did not think foundations should be behind a paywall. He gave talks explaining, without visible embarrassment, that he had spent years believing a theorem of his own that was false, and that this was the reason he was doing what he was now doing. He died on the 30th of September 2017 at his home in Princeton. He was 51. The work is unfinished. It is a live research program with real critics and open problems, and I am not going to tell you it is the answer, because that is not settled and I do not know. What I will tell you is the shape, because the shape is what this whole thing has been building toward. 469 years ago, a man in London invented a mark so that he would not have to keep writing 3 words. He justified it by saying that no two things can be more equal, and for most of the intervening centuries that was treated as a charming remark rather than as a claim about the world. It was a claim about the world. And as far as anyone can currently tell, it is not true. There are degrees. There are kinds. There is structure inside the relation. The relation has a shape. And the flat mark he chose because it was symmetric and simple and easy to set in type concealed that shape for 400 years from everybody, including the people whose entire profession was to look at it. The notation did not just help us think, it also told us what not to look at. And we did not look, because it did not occur to anyone that there was anywhere to look, because the symbol was flat, and so we assumed the thing was flat. That is not a story about mathematics. I want to be very clear about that before I go any further. That is a story about what happens to any mind that inherits a set of marks. Because mathematics is not the only place this has happened. It is just the place where the record is clearest, because mathematics writes everything down and keeps it. Take music. For most of the history of the human species, music was transmitted the way Tartaglia transmitted the cubic, which is to say by memory, from a person who knew it to a person who did not. There was no way to fix it. Around the year 1025, a Benedictine monk called Guido of Arezzo, working in northern Italy, developed the system of lines and spaces that became the musical stave. His claim, which is in his own preface, was that a singer trained on his system could learn in days what had previously taken years, and that a singer could now learn a chant he had never heard. That is the same claim Recorde is making. Avoid the tedious repetition, offload it onto the page, but look at what came next, because it is not a story about efficiency. Around the end of the 13th century, Franco of Cologne set out a system in which the shape of a note determines its duration. Before that, rhythm was not writable. You could indicate pitch, and you could not indicate time, and within a couple of generations of rhythm becoming writable, European music produced polyphony of a complexity that cannot be held in a single head and cannot be coordinated by ear. You cannot have 40 independent voices without a score. Not because the composer is not clever enough, because there is no place to put it. Thomas Tallis writing a motet in 40 parts is not doing something a brilliant enough oral tradition could have done. He is doing something that the page does, and the page did not exist before somebody drew the lines. And then there is the other half, which nobody mentions. Western staff notation divides the octave into 12. That is what it can write. It has no way to record the pitches that sit between those 12, and the musical traditions of most of the world are full of them. The intervals of Arabic makam, the microtonal inflections of Indian raga, the ornaments that live in the gaps. When Western notation spread, along with Western instruments and Western recording and Western musical education, it did not just fail to capture those. It quietly pressured them out, because a thing that cannot be written down, cannot be taught at scale, cannot be published. cannot be standardized, and eventually cannot be defended. The notation did not describe the music, it selected which music could survive contact with it, or take the number system itself, which is the most obvious case, and therefore the one nobody thinks about. Try multiplying two large numbers in Roman numerals. Not as a puzzle, actually try to specify a general procedure. There is not one. The Roman system has no place value, which means the position of a symbol carries no information, which means there is no algorithm, which means every multiplication is a separate act of ingenuity or a session with a counting board. The positional system with a 0 developed in India and set out by Brahmagupta in the 7th century. Arriving in Europe through the Arabic mathematicians and into the Latin West through Fibonacci in 1202 does not make arithmetic easier. It makes arithmetic mechanical, which means it makes arithmetic something that can be done by a clerk who does not understand it, which means it makes commerce at scale possible, which means it makes the modern world possible. The 0 is not a number. It is a piece of punctuation that tells you a column is empty. It is a notational device, and it is arguably the single most economically consequential mark ever made. Or take chemistry. Jöns Jacob Berzelius, in 1813, proposes that each element be written as one or two letters from its Latin name, and that compounds be written by putting the letters together. That is it. That is the whole innovation. And within a few decades, once Cooper and Kekuli start drawing the bonds as lines between the letters, chemists are looking at a picture of a molecule and reasoning about its behavior by looking at the shape of the drawing. Kekuli's benzene ring in 1865 is not a discovery about carbon, it is a discovery about a drawing. He worked out that the arrangement had to close on itself, and the reason he could think that thought at all is that there was a notation in which a structure could close on itself, or take physics in living memory. In 1948, Richard Feynman introduced a way of drawing the interactions of particles as little pictures with lines and vertices. They were not initially popular. Freeman Dyson did the work of showing that the pictures corresponded rigorously to the terms in the underlying expansion, and once that was established, something happened to the field that Julian Schwinger, who had done the same physics by other means and by all accounts, remained irritated about it for the rest of his life, described as bringing computation to the masses. He did not mean it kindly. He meant that calculations which had required his own extraordinary facility with the formalism could now be done by graduate students, by drawing pictures and reading off the terms. That is Whitehead's cavalry charge, exactly. The number of important operations you can perform without thinking about them went up. And it went up for everyone at once. And the field accelerated. Every one of those is the same event. A person, usually solving a local and rather boring problem, invents a way of arranging marks. The arrangement takes over some of the work. The work that used to require the full attention of an exceptional mind now requires the partial attention of an ordinary one. And the field moves. And in every one of those cases, the notation also decided what the field would not look at, and in every case it took a long time for anyone to notice, and in some of them nobody has noticed yet. That is the thing I keep circling and cannot get around. You can measure what a notation lets you do. It is right there, in the output, in the curve. What you cannot measure, from inside, is what it stops you doing, because the evidence of that would be the absence of thoughts, and an absent thought does not leave a gap you can see. It does not feel like a gap. It feels like the edge of the subject. For 400 years, the flatness of two parallel lines told everyone that equality was flat. Nobody experienced that as a limitation. They experienced it as a fact about equality. The limitation only became visible when a machine, which does not know what anyone means and cannot be persuaded, was asked to check the reasoning and refused. We needed something that was not human to see the shape of the thing humans were looking through. Now let me bring this back to you, because I have been circling it for 2 hours and it is time to say it plainly. You have a set of marks, not just mathematical ones. You have a vocabulary, which is a notation for concepts. You have a set of categories you sort experience into, and those categories came from somewhere, and almost none of them came from you. You did not derive them. You absorbed them, mostly before you were 7, from people who had absorbed them, from people who had absorbed them, back through a chain that eventually terminates in somebody who was solving a specific local problem and did not have you in mind. And the properties of that inherited set determine what is easy for you to think, what is hard, and what does not occur to you at all. That is not a mystical claim. It is the same claim I have been making about the equals sign for 2 hours, applied one level out. A compact symbol for a relation makes that relation cheap to handle, and a relation that is cheap to handle gets handled constantly, and a relation with no symbol gets handled rarely and badly and mostly by people who are being paid to specialize in it. You can watch this happen in real time in any technical field you learn as an adult. The first 6 months are not spent learning facts. They are spent learning what has a name. And the experience of learning what has a name is not the experience of acquiring information. It is the experience of a fog lifting off a region you had been walking through blind. And afterwards you cannot reconstruct what it was like not to be able to see it, which is exactly why nobody can tell you what they are not seeing now. I said earlier that you did not think your way to the shelf. You inherited the ladder. Here is the full version of that, which I have been holding since the first 20 minutes. The ladder was built by people who were not thinking about the room. Recorde was thinking about his aching hand. Bacchus was thinking about a key punch with a limited character set. Guido was thinking about how long it took to train a choir. Basilius wanted a shorthand for the printer. Not one of them was designing a cognitive architecture for the species. Every one of them did. And the ladder is not a ladder. It is a set of rungs at particular heights, and there is nothing between them, and the regions it does not reach are not marked as unreached. They are not marked at all. From inside the room, an unreachable region and a non-existent region look exactly the same. The whole of the story I have just told you exists in the record for one reason, which is that mathematics is unusually good at keeping receipts. We know about Descartes' loop and Xylander's uprights and Heragoni's numerals because Cajori went and counted them. We know the equals sign nearly died because there is a 61-year gap in a print record that somebody bothered to maintain. There is no equivalent record for the rest of it. There is no Cajori for the concepts you did not get a word for. And there is one more turn in this, and it is the one that took me longest to see. The reason the flatness of the equals sign was finally noticed is not that a sufficiently brilliant human noticed it. Human beings had 400 years and the best minds of several civilizations, and they did not notice. And when Carlos Simpson noticed something adjacent to it and published a correct refutation, the field did not believe him for 15 years. It was noticed because somebody tried to explain mathematics to something that was not a person, and the thing that was not a person could not do what every human mathematician does automatically, which is to silently substitute the sensible meaning for the written one. The machine took the marks literally. It took them exactly as literally as they had been written, and in doing so, it exposed a gap between what mathematicians write and what mathematicians mean that had been open, unnoticed, load-bearing for the entire modern history of the subject. We did not find the flaw in our notation by thinking harder. We found it by handing the notation to something that could not think at all, and watching it fail in a way that made no sense unless we had been lying to ourselves. Now go back to Southwark. It is the summer of 1558. Mary is dying and does not know it yet. In the King's Bench prison, there is a Welsh physician. somewhere around 48 years old, who has been a Fellow of All Souls and a Doctor of Medicine of Cambridge, and Comptroller of the Royal Mint at Bristol, and Surveyor of Mines in Ireland and, briefly, Physician to a King. He has 9 children. He has written the 4 books that between them will teach arithmetic, geometry, astronomy and algebra to the English language, and one of them will be reprinted 47 times over the next century and a half, and one of them will never be reprinted at all. He is in that room because he insisted, twice, in the face of a man who could destroy him, that 2 columns of a ledger must correspond, and that if they do not correspond, someone has taken something. The state that put him there owes him roughly the sum that put him there. It will pay in 1570. He will have been dead for 12 years. He writes his will on the 28th of June. We do not know what day he died. We do not know where he is buried. The dates in the record contradict each other, and no historian has ever managed to make them balance, which is either a grim coincidence or the last joke in a life that had a lot of them. And in a book that nobody bought, printed the year the court destroyed him, there are 2 short parallel lines. Twins, he called them. Gemmo lines of 1 length. He picked them because he was sick of writing 3 words. Since then, that mark has been written by every literate person on this planet, in every language, in every discipline, more times than any other symbol any human being has ever devised. It is on your keyboard. It is in the code running the device you are holding. You made it yourself, probably today, without a flicker of attention, in the same way you breathe. It very nearly did not survive. It sat in one unsold book for 61 years. It was saved by an anonymous appendix, a country schoolmaster's textbook, and an editor tidying up a dead man's manuscript. It went into a fight against the most famous philosopher in Europe, backed by the best publishing house on the continent, and it won on prestige and geography rather than on merit. And it carried into the modern world a claim about the nature of sameness that turned out, 4 centuries later, to be false, and that concealed the falseness precisely because the mark was so simple that nobody thought to look inside it. That is the object you think with. And now consider what that means about the rest of it, about the marks you use for things that are not mathematics, about the words you have for what you feel and the categories you have for other people, and the concepts your profession handed you in your first 6 months, which you now experience as the structure of the world rather than as a set of choices made by strangers. Somewhere in the ordinary business of your life there is a relation you handle every day that has no name. You deal with it constantly. It has no compact form, so you cannot hold it still. And you cannot hold it still. So you cannot examine it, and you cannot examine it, so you do not experience it as a thing at all. You experience it as the texture of how things are. It is not hidden. Nobody is concealing it. It is simply, for now, tedious to write out. And one day somebody with a deadline and a tired hand is going to get sick of writing it out, and they are going to draw a mark. And if the mark survives the 61 years, and the rival symbol, and the indifference of everyone who could have carried it, then a few generations after that, nobody will be able to think the way you are thinking right now. They will not know that anything was lost. They will look back at us the way you have spent this entire time looking back at al-Khwarizmi, writing his paragraph. 1 square and 10 roots are equal to 39 dirhams, in full, every time, because he had nothing else. And neither do you.